Hi, everyone. Welcome to the second part of the two-section tutorial on power calculation in three-phase transformers. Today, we'll be dealing with more into the reactive power and the parallel combination of the transformers. So let's dive into question number one. It's saying an industrial facility is aiming to improve its power factor from 0.65 lagging to 0.95 lagging. The facility operates at a total load of 800 kilovolt amperes with the original power factor, which in this case is going to be 0.65. To achieve the desired improvement, two capacitors C1 and C2 are to be connected in parallel. The capacitor reactance of C1 is 3 ohms and C2 is 4 ohms. Calculate the total reactive power provided by the capacitors and the reactive power provided by each capacitor. So in order to solve this, we need to consider how the apparent power is related to the reactive power with respect to the lagging factor or the power factor. We know that essentially S equals P plus JQ. However, there is another equation that relates P to S with a factor of cos theta. If you consider that, and there is a Q that essentially is S sine theta. So with knowing S as we're given in this question, we want to find out what is Q. And we don't know actually what sine theta is, but we know actually what cos theta is, because cos theta is the power factor. In order to generate cos theta, we need to modify the second equation slightly, because we know that from math equations and arithmetic, that sine theta can be represented with square root of 1 minus cos theta squared. So that's how cos theta appears in the calculation of Q as well. Now we have S, because that's simply the initial apparent power. And also we know the initial power factor to be 0.65. We can then find out the initial Q or the reactive power. Then we can use the same analogy to find the desired inductive power or the desired reactive power with respect to the ideal and desired power factor. Then the subtraction of these two would be the added reactive power to the system. So in a sense, Q can be calculated for the original case, which is going to be S square root of 1 minus cos theta squared. In this case, S is going to be 800 kilovolt amperes, square root of 1 minus 0.65 squared. This turns out to be around 607 kilovolt amperes. Well, in this case, that's called VAR, because that's the reactive power. Now, we need to go for the calculation of desired Q, because that is when the power factor is going to be the desired value. In this case, the power factor is going to be 1 minus 0.95 in this case, because that is what the question is asking as the desired power factor squared, which takes us to a value of around 249 VAR as well. So this delta between them, delta Q, is around 358 VAR, is essentially the amount of improvement that we're expecting to achieve by employing two parallel C1 and C2. So that's the total reactive power provided by this capacitor. That's the amount of reactive power that is provided by this, and that is a negative value in general that reduces this, the Q. So next part of the question is asking the reactive power provided by each capacitor. We need to be mindful of the fact that those capacitors are going to be connected in parallel with each other. So this would be a rough idea of how C1 and C2 are going to be connected. And there will be specific currents of I1 and I2 passing through each one of those capacitors as well. However, there will be impedances related to these capacitors Z1 and Z2 with respect to their capacitances. In order to find out the amount of the current passing through each one of them, it's going to be, again, the current division, which is slightly different than the voltage division, because the total current, in this case, is going to be multiplied by the Z2 divided by Z1 plus Z2. So that's how the current division is going to work. The current passing through the first capacitor is going to be proportional to the other impedance divided by the summation of the impedances. So if we consider this to be the current that is passing through each one of them, we also know that the voltage across them is going to be the same, which essentially means that the Q is going to be distributed similarly, which means Q1 is going to be Q total times Z2 divided by Z1 plus Z2. So that holds true actually for the reactive power as well. And now for Q1, we have the total Q that is going to be QC, which we just found out that to be the extra reactive power that is going to be the delta Q's 358 var divided by times Z1 turns out to be 3 ohms. I'm gonna actually write it here. And Z2 turns out to be 4 ohms. So essentially Q1 is going to be multiplied by 4 divided by 3 plus 4. So if you simplify this, you get to a number of around 204 var. Similarly, Q2 is going to be QC, or the total, times this time the other impedance, 3 divided by 3 plus 4, which is going to take us to around 153 var. So that's how the total reactive power brought by these two parallel capacitors are going to be calculated, and the load on each one of them is going to be distributed as follows. So let's dive into question number 2. The second question is, a factory operates two machines, machine X and machine Y, connected in parallel to a single electrical supply. Machine X draws 120 kilowatts at a power factor of 0.75, while the machine Y draws 180 kilowatt at a power factor of 0.85, lagging. Remember that these two machines are in parallel, and they are operating at different levels of the power in terms of the power factor, as well as the lagging level, or the power factor. Okay, so let's dive into question number 2. The second question is, a factory operates two machines, machine X and machine Y, connected in parallel to a single electrical supply. Machine X draws 120 kilowatts at a power factor of 0.75. Machine Y draws 180 kilowatts at a power factor of 0.85, lagging. Calculate the combined power factor of the factory's load and the total real power consumption. So we're dealing with actually two parallel combination of machines X and Y with different power factors and different generated powers. In order to find out the combined power factor of the factory, we need to also consider the reactive powers of each machine. and then consider the total apparent power of machine X and machine Y, and then consider the total power factor. So essentially, we are now having S1 that goes for P1 plus JQ1. And in this case, we know information about the power factor and also the information about the P1, which is 120 kilowatts. In this case, in order to find out the Q of this, we know that from the previous expressions, P1 equals cos theta S1 and Q1 equals sine theta S1. However, in order to find sine theta, we need to employ 1 minus cos theta squared S1. And we already know that in terms of the information that we have, we know P1 over here as well as cos theta, but we don't know S1. So S1 is going to be simplified as 1 minus cos theta squared P1 divided by cos theta. So that is how Q is going to be represented with all of the given information of the question. We have P1 as 120, we have cos theta as 0.75. So if you plug them in, we have square root of 1 minus 0.75 squared times 120 kilowatt divided by 0.75. You get to a number of around 105 var. So that is the reactive power of machine 1. So essentially, machine 1, S1, can be represented, in other words, as 120 kilo plus J 105 k var. Now let's move on to the second machine. We're going to actually employ the same line of thought for Q2, which is going to be, again, borrowing the same equation, 1 minus cos theta squared, P2 in this case divided by cos theta. I remember that these thetas are going to be the second version, and we know that cos theta in the second time is going to be 0.85, and P2 is going to be 180. So employing them is going to be 1 minus 0.85 squared divided by 0.85 times P2, which is 180 K. You get to a number of around 111 K bar. And essentially S2 now becomes 180 K plus J 111. And essentially, that's the total power that is going to be considered in our case. So we also need to be mindful of the fact that the reactive powers are going to be positive here, since we're dealing with lagging system and they are inductive. So in a sense, let me just point out a minor point here, that in the lagging system that we're dealing with mostly inductive circuits, the current actually lags the voltage, and that's why we're dealing with positive reactive. So Q becomes positive. Conversely, Q becomes negative for the leading circuits that uses capacitors. And in this case, the current leads. And that's why they are called the leading. So the way that actually we have written these Q's to be positive, they denote the factor that we're dealing with a lagging system. However, Essentially, the rest of the question now becomes the consideration of the fact that the total apparent power is the summation of individual apparent powers that we have here. And in that case, S total equals S1 plus S2. And in the rectangular format, we have 120K plus J105K plus 180K plus J11, 111. So I'm going to actually highlight them so that it would be easily tracked. So S1 is here, and S2 is here as well. So these are going to be summed up. The total S then would be around 300K plus J 226K, 216K indeed. So now that we have the total apparent power, the combined power factor of the factory can be calculated as follows. So we know that cos theta is going to be P divided by square root of P squared plus Q squared. So essentially, P is going to be divided by the magnitude of S, which in this case is going to be P squared plus Q squared. And P and Q's are these values. So if you plug them in and simplify this, you get to a power factor of around 0.81, which is lagging again. So essentially, combination of a power factor of 0.75 and 0.85 turns out to be around 0.81, which is somewhere in between them. So that's how we could get to the total power factor with respect to individual power factors and the calculation of the apparent power as well. So the third question, now the question is asking two transformers A and B are connected in parallel. The total load supplied by them is 600 kilovolt amperes at a power factor of 0.8 lagging. If transformer A supplies 360 kilovolt amperes and with 0.8 lagging power factor at an impedance of 0.2 plus J 0.6 ohms, calculate the apparent power supplied by a transformer B and its power factor, assuming its impedance is 0.25 plus J 0.75 ohms. So we're now dealing with two transformers, A and B, that are combined together, and the total supplied power is going to be 600 with a specific power factor of 0.8. Now we're given the information of one of them, and the question is asking about the power factor and power of the other one. So essentially, if you write down the information that we have, the total power or load is going to be 600 kilovolt amperes, and transformer A is going to supply 360 kVA at 0.8 power factor. The apparent power factor, the apparent power by B then is going to be SB is going to be S total minus SA. And in this case, 600 minus 360, which is going to be 240 kVA. So now, in terms of the power factor of transformer B with respect to power factor of transformer A, if you take a look at the impedance of transformer A, we can find out that the impedance is going to be related in terms of the imaginary part and the real part by a factor of 3, which deals with the same ratio of the imaginary to the real of transformer B as well. This ensures that the amount of the lagging or leading is going to be the same for transformer A and B. So these two transformers are in phase with each other. And we can also assume that the power factor for them are going to be equal because the impedances are going to be with the same ratio. In that case, the power factor of B is going to be the same as power factor of A because of the impedance ratios. And in this case, both of them are going to have 0.8. So essentially, transformer B is working with a parent power of 240 kilovolt A and the power factor of 0.8. So here is the exercise that I have designed for this part of the power calculation in three-phase transformers. It could be solvable with respect to the topics that we discussed in this video. Feel free to leave your comments and questions below the video and hit like and subscribe to the channel if you like more videos. Have a good one.